Hello everyone, this is Jim Corkins. We're continuing on with Kinematics, and we are at 1.03, and today we're going to talk more about what are motion diagrams. And we've been using these before a little bit with the graphing and talking about average speed and displacement and things like that. But now we're going to talk about it in more detail so we could really get into how do you represent velocity vectors related to position and also time. Okay, so if you haven't done the reading, please go ahead and do so in those textbooks. The reading is listed there, and please begin your homeworks. Okay, so motion diagrams, or another word for it is particle diagrams, are the same thing. And so what a particle diagram is basically it's the center of mass. It's the infinitesimal center of mass of any object. Okay, so that's represented by a dot. Okay, so motion diagrams, we're going to put little dots on these horizontal axis on the x-axis, and we're going to represent that motion with little dots, and that represents the center of mass of the object. And we're not going to get more into what is center of mass until we get into rotational motion and things like that. But anyways, so what is a motion diagram? Okay, well, suppose you were taking a picture, and I'm going to mark up this document. So to mark up the document, to go to comments, and then this will pop out when you hit comments right here, and then you could push it back in right there, and then you hit, so there are some tools here. You've got your drawing tool, you've got your eraser, and you could draw shapes. And you could also change the color of those tools as well. So suppose you were taking a picture, okay, and so you're standing right here at the 0 meter mark. Right where this palm tree is. And you were taking pictures, and you took the first picture, and the first picture will be taken at 0 seconds. And then 1 second later, you took another picture. And another second later, you took another picture. And then another second later, you took another picture. Okay? Now, when you overlay each one of these pictures on top of each other, it looks like this. Okay? So here is the 0 meter mark. Okay. The object started out over here at the 0 second mark, and this is 1 second later. This is related to this picture. The next picture is going to be the 2 second mark. And at the 3 second mark, now you can see that the car is right on top of where the palm tree is. Well, this is essentially a motion diagram or particle diagram, okay? Typically at the bottom, you represent the positions of the object, okay? And you have to represent positions relative to a starting point. And typically we put the stationary observer at the 0 meter mark, okay? Okay. And we represent the starting positions at the 0 seconds mark. So this is 0 seconds, 1 second, 2 seconds, 3 seconds. And so the positions are going to be relative to this, and usually to the left is going to be the negative x direction, and to the right will be the positive x direction. Okay, so we're at the center of, we're at 0 meter mark, right where the you're the stationary observer, and you're right next to this palm tree. And I'm just going to arbitrarily state this. This is to the left, so it'll be negative 10 meters to the left, and negative 20 meters, and negative 30 meters. I just chose those. I don't know what the actual positions of the car was at those points, but I want to make it something serious. And so what we have here now is we can now draw vectors. We can now draw the velocity vectors, right? Since velocity is a relationship of position, or rather displacement, to time, right? From the 0 second mark to the 1 second mark, the object was starting here and then it went to there, okay? And so you could see that its displacement is going to be negative 20 meters minus a negative 30 meters over 1 second minus 0 seconds, right? So the velocity from the 0 to 1 second mark is going to be the displacement over time, and that is negative 20 meters minus the negative 30 meters over 1 second minus 0 seconds. So that's going to work out to be, what is that? Positive 10 meters over the period of 1 second, right? So that it looks like this object is traveling at a speed of 10 meters for every second, and its displacement is in the positive x direction, right? Even though its positions, again, from that first or that second activity that we were on, we were talking about how position is different from velocity. You could have a negative position but have a positive velocity, and so this is a great example of that. You have an object that is traveling, that's started out at negative 30 meters and is now going to be at negative 20 meters. So it's traveling to the right, which means its velocity is going to be positive, okay, even though its position is negative, right? Well, if we continue on with this, we could represent the next velocity vector, which is also negative 10 meters minus a negative 20 meters over 2 seconds minus 1 second. So this is also going to be, it's traveling to the right 10 meters for every second. And then finally, the last velocity vector is going to be the same. It's traveling to the right at 10 meters for every 1 second. Okay? So these motion diagrams are a great way to represent velocity, position, and displacement, as well as time. And so the start time, I just want to reiterate this. I'm going to use a different color. The start time always occurs at 0 seconds mark. Okay? So in these motion diagrams, you're going to look at the top part to see the 0 seconds mark, and that will be the start of the object's motion. Okay? The end of the object's motion is just the last number, the last time that appears there. The positions of the object should appear at the bottom, and they should be the actual positions. So they'll be represented in typically in meters, and they will be positive or negative numbers, and they're representing the positions as if it's along an X or Y number line. Okay, and so here are some little rules that were kind of related to this. An object can have an object with a position greater than 0 is going to have a positive, is going to be to the right, so it'll have a positive position. An object with a position less than 0 will be to the left of the origin. Vectors pointing to the right will have a velocity greater than 0, meaning it's got a positive velocity, so that'll be pointed to the right. Objects, velocities that are less than 0 will be pointed to the left. And so we're assuming that our number line means to the right is positive and to the left is negative. Or up is positive and down is negative, okay, in the Y directions. All right? So let's try to apply what we've learned as far as motion diagrams, motion graphs, and also creating prediction equations to represent that motion in one problem right here. So here we go. You have an object right here that has a motion diagram illustrated, and this object is going to have positions that are going to be to the right of the origin. So you're standing right here at the 0 meter mark, and so these are represented in meters. Sometimes they don't put the units on there because they put the units right here. What I want you to do is I want you to evaluate this motion diagram, okay, and just briefly describe what is happening. Describe the type of motion that you're seeing as, moving to the right, moving to the left, and try to eyeball or estimate the velocity of the object. And also describe its beginning position, its end position, its overall displacement, as well as the overall period of time that it's moving. And that's what you're supposed to do here when you're describing the object's motion. So now you're supposed to try to really calculate the velocity of this sprinter. And then what I want you to do is I want you to graph this motion in a position versus time graph. Okay, so you're going to have to put in the units. I've put in the top unit here, but you're going to have to actually represent the time and put in little tick marks here and graph it. And then what I want you to do is I want you to create an equation, a prediction equation related to the graph and also related to your motion diagram that will accurately predict this object's motion. Okay, so take a moment, pause the video, and try that out. All right, well, hopefully you've actually tried this out, and we'll see what we're doing here. Well, let's interpret the motion diagram, okay? So it looks like the origin is here, and this is where we're standing. And it looks like it's broken up by, in terms of 10 meters. So this is 10, 20, 30, 40, 50 meters. And it looks like the object started out here at the 0 seconds mark. So this is where it starts, and this is where it's ending. Okay. And I'm going to draw some vectors. So it looks like the object is moving to the left. So in the very first second, it moved to the left. And it looks like it's moving to the left 10 meters over the period of that 1 second. So this looks like its displacement is going to be 10 meters for that first second. And then after the second time, it looks like it's also moving to the left another 10 meters over the period of a second, and so on and so forth. So I like to mark up my motion diagrams. That didn't work out there. Negative 10 meters over the period of 1 second. So I like to mark up my motion diagrams and actually put in the velocity vectors, so that would actually help me describe what's happening. So this looks like an object traveling at a constant velocity, meaning it's not speeding up nor slowing down. It looks like it's just got the same speed to the left. To the left. Okay? Starting at 50 meters. I'm not looking for a specific choice of words here, just something brief to describe what you think is going on. And as long as you have constant velocity and the object's moving to the left, that's fine. You don't have to go too in depth on this, right? Just want to get a feel for what is happening. Well, since the object has the same velocity vector all over time, let's go ahead and figure out what the displacement is, because displacement is the velocity, right? It really is the leading point into velocity. So I'm going to go with its final position minus initial position over the final time minus the initial time. And since this velocity is constant, you could say this is its starting position. We could calculate its end position. And then in this case, its average speed will be its instantaneous speed. So these little vectors are its instantaneous speeds or instantaneous velocities at each one of these points. But in this case, since it's not speeding up nor slowing down, its average velocity will be its instantaneous velocity as well. And so we could use whatever time increments here as long as we're consistent. So I'm going to just use the initial thing right here. So it's displacement. Let's do its overall. It started out it ended at the 10 meter mark. Okay. At 4 seconds. And it started out at the positive 50 meter position at 0 seconds. So what we could say is that the object is going to be 10 minus 50, so that's negative 40 meters over the period of 4 seconds. By dividing this out, 40 divided by 4, and this is supposed to be seconds, is going to be negative 10 meters over the period of 1 second. So it's it's instantaneous speed. And I should have put a delta t here. Its instantaneous speed is its average velocity. Its instantaneous velocity is its average velocity. Okay. All right. Well, let's put some increments on this. I'm going to use black to represent the increments on the graph. Okay, I'm going to try to divide this up. This will be 10, 20, 30, 40, 50. So this is 10 meter mark, 20 meter mark, 30 meter mark, 40 meter mark, and I wasn't even, but I'm just doing my best. This is 0 meter mark and also 0 seconds mark. 1 second mark, 2 second mark, 3 second mark, 4 second mark. 2 seconds, 1 second. Okay. So at the time of 0 seconds, the object started out at the 50 meter mark at 0 seconds. Okay. So that's like its y-intercept. Okay, it's the initial position we're going to be using as a y-intercept. And then at the 1 second mark, so that's the 0 second mark is 50 meters. At the 1 second mark, it's going to be right here. See, 1 second, 40 meters. The 30 meter mark, I'm going to try to space this as best as I can. So this should look like a straight line, since a straight line means its instantaneous velocities are not changing over time, so it's going to be a straight line. The slopes should be the same. The instantaneous slopes at each one of those points should be the same. At the 3 second mark, it's at 20 meters, and at the 1 second mark, it's there, right? So this should make a nice straight line, ending right here at the 10 meter mark. Okay, that looks pretty good. Well, the general equation for a curve, a linear fit, is y is equal to mx plus b. Well, we're trying to predict horizontal positions, so our y-axis is going to be the horizontal motion, okay, the horizontal positions. In a position versus time graph, the slope will be the velocity. In fact, it'll be the initial velocity, which is equal to the final velocity. So constant velocity is just this. The horizontal axis is time, and that'll be plus, and Let me change this to a time. That should look like a T. And my pluses sometimes look like T's. I'm very sorry. And times the initial position. Well, here we go. That's the general equation that we're working with. Well, here we've already figured out our velocity, and our constant velocity is going to be negative 10 meters per every second, delta t, and that's going to be plus the initial position, which occurred at the 50-meter mark. So this is the prediction equation that we're going to be using here that represents the graph and also represents the motion diagram. Okay? And what I like to do is just try to put in some numbers to see if it works. What is the object's position at the 2-second mark? Well, that's going to be negative 10 meters per second at the 2-second mark. And that's actually 2 seconds minus 0 seconds, but plus 50 meters. So this is 2 seconds times negative 10 meters per second, which is going to work out to be negative 20 meters, plus 50 meters, which is going to work out to be 30 meters at the positive 30 meter mark. So that means at the 2-second mark, that should work out to be 30 meters. Perfect. So this is accurately predicting, this linear equation is accurately predicting the motion in our graph. And then to just make sure, our 2-second mark, it is at the 30 meter, at the 2 seconds, it is at the positive 30 meter position. So it's predicting all of these. Okay. So the point is, you could actually use vectors and positions to actually create a linear equation. We could have just used this to create our linear equation too, right? We didn't have to actually create this graph. So pretty cool. All right, let's try another one. Here's two motion diagrams of two different objects, a car and a bicycle. What I want you to do is I want you to go ahead and I want you to create two linear equations, one for the car, one for the bicycle, that describes what's going on. So rather than the last exercise where you analyze the motion here and describe the motion in the motion diagram and then create a graph and then create the linear equation, I want you to actually try to jump from the motion diagram and create a linear equation. Okay? So go ahead and pause the video, describe what's happening with the car, describe the motion, and try to create a linear equation based on what you're seeing. Okay? Pause the video now. Okay, well, if you're looking at this, the car looks like it's moving from the 0-second mark to the 1-second mark. Okay. And then from the 1-second mark to the 2-second marks. From the 0-second mark to 1-second mark, it looks like it travels from the positions of 0 to positive 40. So these are all the positive positions. It means it's to the right of the origin. And this motion seems, the car seems to be moving to the right at the same increments, right? It moves 40 meters in 1 second, and then from the 1 second to 2-second mark, it moves another 40 meters. And from the 2 seconds to 3 seconds mark, it moves another 40 meters. So it looks like this object's motion is going to be a displacement of positive 40 meters for every second. So it's got a speed of 40 meters to the right for every second. The bicycle, I'm going to use red to describe the bicycle. The bicycle is moving to the right as well, right? Its initial position here, 0 seconds tells you its initial position, which is at 0 meters. It's moving to the right, and it moves to the right 20 meters, so its displacement is going to be 20 meters for every second. This is 20 meters for every second. Another 20 meters for this last second. Okay? Right? And just by looking at the initial starting point, 0 seconds mark, and look down, and it's at the 0 meter, both objects started out at the 0 meter mark, okay? So that tells us what our y-intercept is, or our initial position is, okay? So now we're going to put both of these objects into this format, okay? So let's try the car. We're going to predict final position in the x-axis, so we're going to predict a horizontal final position of the car. The car had a velocity of 40 meters for every second to the right. Delta t is the time interval, and it looks like the car started out at 0 meters. And you could just say positive 40 meters per second delta t, positive 40 meters for every second delta t, and not put this part. But I like to always put in what its starting position is, okay, just to be careful. So the car's velocity is positive 40 meters for every second, delta t. And so we could actually try it out. Let's just say if we could predict the position at the 2 second mark. Hopefully it'll wind up being 80. So the car was moving from 2 seconds minus 0 seconds plus 0 meters. So the cars had moved from 0 to 2 seconds at a constant velocity of positive 40 meters for every second. So this is going to be 2. This is going to work out to be 2 seconds. 2 seconds times 40 meters over 1 second is going to be 2 times 40. 2 times 40 is going to be 80 meters plus 0. So this is going to work out to be 80 meters. And so at the 2 second mark, it does have a position of 80 meters. So this is an accurate prediction equation, okay? All right, let's try a prediction equation for the bike. The bike was also moving to the right, but at half the speed of the car. So its displacement was 20 meters, and its velocity was positive 20 meters over every second. Delta t, and it also started out at a position of 0 meters. So let's try to make sure, again, let's make sure this is going to work out. Let's try this again, 2 seconds mark minus 0 seconds mark, okay? So again, 2 seconds minus 0 seconds is just going to work out to be 2 seconds. 2 seconds times 20 meters over 1 second is going to be 40 meters plus 0, which is going to be at the 40 meter mark. So at the 2 second mark, the bike, right here, 2 second mark for the bike is over here. It's at a position of 40 meters. Or, I'm sorry, I should have been using feet this entire time. Darn it! It's always in the details. Let me erase this. Oh boy, gotta erase all the meters. I put figures. I made that small mistake, and I realized it right at the end. I'm going to just write in feet to everything. I apologize about that. I should have checked my units. It's a good lesson for everybody. And these should be feet as well. And then these should be feet. Feet. And then feet. Okay, well, all right. I hope you learned a little bit from my mistake. I apologize that you're probably screaming at the screen, Jim, that should be 40 feet. That should be feet, not meters. but there we go. All right, this should be feet as well. All right, there we go. Now, this is accurate. Anyway, so you could use, the point is you could use motion diagrams, using vector addition, using vectors and position to actually create your prediction equations too. You don't have to jump to the graph and then create a linear equation from the graph. So here's another prediction, another practice problem, and this is more of a just real quick multiple choice or matching. What I want you to do is I want you to match the motion diagram and to the graphs and also to the prediction equations. And so I want you to match numbers to letters to Roman numerals. Okay? So go ahead and try this out and see how well you do. And pause the video now. Okay, well, let's look at this. So here we go. We have an object moving, and it looks, if these are in terms of seconds, these are in terms of seconds, this is going to be the start, so that's always the 0-second mark. Okay, and I'm just going to arbitrarily say this is 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. And here we have another object traveling the opposite direction. So this will be 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and then 5 seconds. So it looks like A is going to be traveling to the right at about, so its displacement vector is going to be to the right 10 meters. So 10 meters for every 1 second. And it looks like it's doing that consistently throughout. 10 meters for every second. Positive 10 meters per second. And it started out at a position of 0. And I'm going to now double check. This is going to be meters. So I'm going to put meters on this part right here just to make sure. To keep me from making mistakes like I did last time. I hope you learned from that. I did. It looks like B is traveling to the left, and it's also being displaced 10 meters, but that's going to be to the left. So this is going to be negative 10 meters for every second. Negative 10 meters for every second. And it looks like it's starting out at 0 second mark at the positive 50 position. 10 meters per every second. Negative 10 meters. So I like to mark up my documents, as my motion diagrams, as much as possible to maximize my information, right? So it looks like A's got a positive 10 meters per second, and it started out at its initial position was at 0 meters mark. So it looks like A is going to be matched with B. A is going to be matched with number 1. And I'm going to be using B is going to be red, and that looks like it's matched with number 2 there. Okay. Now, a positive velocity is going to be a positive slope in a position versus time graph. So that looks like A is also going to be matched with Roman numeral 2, and it does start off at the 0. Its initial position is 0 meters, and its final position is 50 meters, right there. And it's gonna take what 5 seconds to get there. Okay. The B object looks like it starts off at 50 meters and it ends at the 0 meter mark, and it ends at 0 meters at the 5 second mark. So it looks like B is going to be matched with Roman numeral 1. So B is going to match up with number 2, and it's going to be matched up with Roman numeral 1. And it looks like A is going to be matched up with number 1, and it's going to be matched up with Roman numeral 2. Okay. How did you do? Did you make any mistakes? And what was nature of mistakes? Was it matching it up to the diagram? Was it matching the diagram to the equation, or was it matching the diagram to the graph? What do you think? And where it was it the slope that you had a problem with, or was it the initial position? Okay. Let's try another problem. Here you have here you have another problem where you have an object starting out here at the 0 seconds mark at -30 meters, and it's going to be moving to the right. And I'm assuming these are traditionally these dots are spaced out at the 1 second every second. So I'm just going to mark this up. So it looks like this object is going to take, make sure also that you start counting at the 0 seconds. Don't start counting at 1 second mark. In physics and most sciences, you start counting at the 0 second mark, and 0 second is your initial time, which will be also your initial position at that time. So it looks like you have an object traveling to the right, and it's going to take 6 seconds. It's going to start off at the -30 meters mark. And then it looks like something happens at the origin, and the motion changes. And now it's got a positive position, and something's happening. So what I want you to do is interpret this motion diagram and translate it to a position versus time graph. Okay, and make a choice as to what you're seeing. Please pause the video now and attempt this problem. Okay, here we go. So it looks like the object is traveling slower until it hits the origin at the 0 seconds mark. And then it starts traveling faster, okay? So how do I know it's slower? Well, if you look at it this way, I'm going to just put numbers to this, and I'm going to say that this is in terms of meters. And it looks like its speed almost doubles, because it looks like this line, this vector here from the 3 to 4 seconds mark is twice that of these vectors, right? From the 0 seconds mark to the 3 seconds mark, it looks like it's traveling at a constant velocity, and I'm going to say it's going to be -20 minus a -30, so that's a displacement of a positive 10 meters over that first second, right? So it looks like it's traveling at positive 10 meters per second, positive 10 meters per second, positive 10 meters per second. And then something happens, and now it looks like the size of the vector has doubled. So now it's traveling twice the distance for the 3-4 seconds. But it's still traveling to the right, and its displacement is going to be -20, is going to be that should be a positive 20 minus 0 from 4 seconds minus 3 seconds. So that's going to be -20 meters over that second, the 3-4 second mark. This is going to be 30. This will be 40. And this will be 50. And then 60. So this now looks like it's got twice the displacement that it did before, and thus it's going to be traveling at twice the speed. So it looks like this, if we're going to draw a position versus time graph to represent these velocities, it looks like it's going to be a shallow or somewhat level velocity. And then from the 3 seconds to 6 seconds mark, it's going to be a much steeper velocity. In fact, it'll be twice the slope, or twice the steepness. Okay, so it's going to go from level to steep. Well, here's what we have, and also, whoops, I also should have mentioned that I gotta actually be a little bit more accurate in what I drew here, because this, it actually was in the lower part of a position versus time graph as well. So while from the 3 to 6 seconds mark, okay, it was above the 0 mark in the x-axis. From here to here, it was below the 0 mark in the x-axis. So this is the 0 mark right here, and this is occurring at 3 seconds. So it's got a shallow slope, and it's in the negative part of the position versus time graph. Well, when it hits the 0 mark here, at the 0 meter mark, it's now got its positions are in the positive part of the position versus time graphs. Well, we're going to be looking for an initial line, so I'm going to break up these guys, and we're going to interpret each one of these separately. Okay, so this first line shows a a very steep. So this is going to be a positive position, and it's going to be fast. And then it goes slow, but it's positive position. So this graph right here is actually showing exactly the opposite of what's happening here. This object starts off as slow, and then right here it goes to fast. And its position is negative initially, and its position is positive after. So this is A is the exact opposite, so A is incorrect. Now B is actually showing it does have a negative position in the beginning, so it's got negative positions in the beginning, but this is fast. And then it has positive positions afterwards, and it's slow. So B is also incorrect, because we're looking negative and slow and positive and fast. Okay. C looks like it's showing a constant velocity, where it's got a velocity. See these little slopes here? It's the same as the slopes over here, but it does show negative initial position and positive final position. But since it's not traveling at a constant velocity the entire time, it's got a slow velocity and then the fast velocity. So it's sped up a little bit. Okay, so C is incorrect. Well, D shows a slow initial velocity, but in the positive positions, and then it shows a fast velocity in the positive positions. So it does show slow then fast, but its initial position was in the negative part. So D is incorrect. E is showing it's got a negative initial positions, that is slow, and then it's got positive final positions that are fast. So E looks like the best answer. How did you guys do? Did you try interpreting those graphs just like I did? Let's move on to the other problem. But first, let's talk about our tactics to drawing a motion diagram. So what you want to do when you go to draw a motion diagram, you're going to want to go ahead and establish the coordinate system as the x-axis or the y-axis. Typically, we're going to have left-right as the x-axis, and up-down is going to be the y-axis. And then what I want you to do is I want you to actually label your x-axis. So what I'm going to do is I'm going to draw the x-axis. So in this case, we're, here, this is going to be positive x, this is going to be negative x. And I'm going to establish a coordinate system, and just for right now, I'm arbitrarily setting the center of this as 0 meters, right? And then we're going to establish tick marks, and here we're going to actually put in the positions as positive 10, positive 20, positive 30, positive 40, positive 50, and this is going to be positions in terms of meters. And then we're going to put in the negative positions, right? Negative 10 meters, negative 20 meters, negative 30 meters, negative 40 meters, negative 50 meters, okay? And then what they want you to do is show the beginning of the motion and the end of the motion. So we're going to just say this is going to be a blue object, okay? And let's say it starts off here at the 40 meter mark, right? So its initial position is going to occur at the 0-second mark, and then let's say its final position, it ends here, and it takes 3 seconds to get to here. So notice I've sketched it out, okay, as best as I can. It started here, it ended here, so I'm associating it with a position but also a period of time. And the final time is occurring here at 3 seconds, and it's at a position of -20 meters, okay? So in between here, you're going to have like a 1-second mark and a 2-second mark, right? So let's go ahead and put those positions here. So in the next part, I'm listing the known information, and I've just kind of made this up from my head. So you're going to list as much of the known information as you can. And then finally, what we're going to try to do is we're going to actually try to go ahead and draw our vectors and what quantities that are important related to this, okay? So typically you want to draw a vector from the 0-second mark to the 1-second mark, and I'm going to use red, okay? And those are going to be the vectors pointing from in terms of the time increments, 0 seconds to 1 second, or 1 second to 2 seconds, 2 seconds to 3 seconds. So in a way, your vectors are drawing in the direction of time, but those will also then be related to positions, right? And so after you've done that, you want to look at your displacement of your object. So we're now talking about numbers 5 and 6 here. We're going to list as much of the known information as we can. Well, this object is starting out at positive 40 meters and it ends at positive 20 meters. So that displacement is going to be 20 meters minus a positive 40 meters, which is going to be a -20 meters. And that occurred over 1 second minus 0 seconds. And so that's going to be -20 meters per second. Well, this is a constant velocity, so this is also going to be 20 meters for that time increment of 2 seconds minus 1 second. And then finally, the same thing. Sorry, I didn't do a very good job of drawing all these vectors the same size, but they're supposed to be the same size vectors, okay? And so here we have maximized our information. So from looking at this, you could easily just say, well, I'm going to draw my equation up here. We're predicting final position. Well, this object is traveling at positive 20 meters for every second, delta t, and it started out at an initial position at 40 meters, and how I know that is I look at the 0 seconds mark. So positive 40 meters, okay? And so it's really great. These motion diagrams are really great because you could easily just look at the information and look at the 0 second mark occurs at 40 meters, and that goes right here. And then I'm going to use my displacement over time. As long as this is constant velocity, the average velocity will be equal to the instantaneous velocities. So these vectors I'm drawing are the instantaneous velocities. And that will go right there. And I actually made a mistake. That should have been -20 meters. Okay. So after you do your equation, now you could double check this. This should be -20 meters per second. Let's see if it predicts our 1 second mark. Actually, let's do 2 seconds. Okay, so put this is going to be 2 seconds minus 0 seconds, right? So that'll be 2 seconds times a -20 meters over 1 second. So that's going to be -40 meters plus 40 meters, which is going to be 0 meters. So at the 2 second mark, I should be at 0 meters, and it does predict it. Anyways, this is a great way to represent velocity and speed and use that to create your equations too. So I just wanted to give you a bunch of tools that you could use to envision motion, okay? So now let's actually do a problem, okay? Let's do a problem and let's apply what we've learned. Alice is sliding along a smooth, icy road on her sled when she suddenly runs headfirst into a large, very soft snowbank that gradually brings her to a halt. Okay, gradually brings her to a halt. So that sounds like she's going to be slowing down. Show and label all displacement vectors. Okay, so let's draw this. Okay, let's try to draw a particle. So let's say Alice is going to be moving along at a constant velocity because she's sliding on a smooth, icy road. So that tells me that there's no friction. So she's going to be moving at a constant velocity. But then something happens right here. So this is where she hits the snowbank. Okay. And I will say this occurs where the snowbank is. I'm going to leave some room so I could draw this. So let's just say she's moving along here and she hits the snowbank. So I'm making these equally spaced. So now she begins to slow down. So I'm going to say this. That means if she's slowing down, her velocity vectors, and I'm going to use red to represent her velocity vectors, are going to be the same size prior to her hitting those banks. So this is going to occur at, use blue to represent the time. So I'm going to say she's got 0 seconds, 1 second, 2 seconds. So she's moving along, and then all of a sudden she hits the snowbank. And now she's going to slow down. Well, slowing down tells me that her velocity vector is going to be getting smaller over time. Or rather, you could be saying this, her displacement vector is going to be getting shorter and shorter and shorter until she comes to a stop. So I'm going to say this, after she hits the snowbank, her position is going to just be a little bit shy of that amount, right? And then a little bit shorter, right? There, and now she's a little bit shorter, and then 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 finally stopped. So I'm going to say she comes to a stop right here. And so from here to here is constant velocity. Then she hits the snowbank, and then she's going to start slowing down, which means her displacement vector is going to be coming to a stop. Slowing down. So her displacement vector is going to be coming to a stop, and this is slowing down. And I'm going to go ahead and draw those vectors. Her displacement vector is hopefully getting smaller over time. And then it's just a really small vector there. Okay. And then I'm going to draw her time increments. 4 seconds, 5 seconds, 6 seconds, 7 seconds, and then finally at the 8-second mark she comes to a stop. Okay? And then I'm going to go ahead and draw this. I'm going to actually say this. We were standing at the snowbank, and I like to use, for some reason I like to use whole numbers, and let's say she was going absurdly fast. 10 meters per second is really fast, so she probably got saved by the snowbank. I'm going to try to put in, so let's say here she's at the positive 8 meters when she starts slowing down, and then this is going to be the positive 10 meters, and this is 20 meters, and this is 30 meters. So she comes to a stop at the 30 meter mark. But her incremental positions are going to be, this is going to be 10 plus 20, so this is 15 meter mark. and this is going to be the 22 meter mark. How's it 22 meters? And this is going to be 25 meters. So I try to put in all the incremental units as I can to kind of tell this story. We'll try to relate this story to an actual motion versus time graph. And so what you could see here is that she's got a constant velocity. She hits a snowbank, and how I know it's a constant velocity is she's got the same displacement vector over each time increment. And then when she hits a snowbank, she's going to start slowing down. Okay, and that means her displacement vectors are going to get shorter now for each one of these 1 second time increments. Okay, so each one of these 1 second time increments, she's got shorter and shorter displacement vectors, which are those red vectors. Okay, well, let's check our drawing and see what they've got. And it looks like they have something very similar to what we have. Okay, they've got their constant velocity vectors. Okay, and then they hit the snowbank, and then they actually start drawing their displacement vectors, or velocity vectors rather, displacement vectors, getting shorter and shorter and shorter over time. Okay, well, what we're talking about here is actually a combination of constant motion with this. When you speed up or slow down, now that is called accelerated motion. Okay, accelerated doesn't necessarily mean where you're speeding up. That means it's just got some kind of acceleration vector applied to this. Okay, so we're going to go more into accelerated motion in section 1.1. Okay. But I just wanted to take this time to actually kind of get ready for it, okay? And so I hope you learned a lot about this position versus time graphs, particle diagrams, and how to create equations, prediction equations from all this, okay? And how to represent that. And also take a story and then translate it into a particle diagram, which you could then relate to equations and graphs. All right, so hopefully you learned a lot. All right, see you next time.